you very much for coming to my defense, and thank you all my committee members to come. So my dissertation title is Cognitive Radio Networks, Resource Allocation and the Effect on Users. As you can see, there are major components in my dissertation. So this is the outline. This is the outline of my dissertation. So the first part is a framework for distributed resource allocation and automation control. We propose a framework named Cognitive Digital Home, and we study the resource allocation problems there. And the second part, and also a novel part, is the effect of end-user behavior on wireless random access. We try to study the role of prospect theory in wireless networks. And the third part component is based on the second part, and we try to further study the role of prospect theory on data pricing, wireless data pricing. And in the fourth part of my talk, I will show you all some future work based on my dissertation. So the first part, distributed resource allocation in CDH. So this is a general plot for current home wireless networks. So we can see there usually are two layers of wireless networks. The first layer is wireless home automation networks. We have many sensors, like medical sensors, detectors, and smart fridge sensors. This device can all provide a convenient lifestyle to the people in the house. And a second layer of networks is the wireless home entertainment networks. And actually, traditionally, we have the wireless Wi-Fi, web data serving, and also now we have wireless HD TV and wireless HD streaming. It's kind of industry standards for current home entertainment networks. So as a result, we can see the features of current wireless home networks. There are three major features here. The first one, also the most important one, that we see a multiplicity of radio access technologies here, right here. So we will see that Wi-Fi and Bluetooth, this legacy technology in a home, and maybe in the near future, we will also see some 60 GHz radio devices and maybe TV white space cognitive radio devices in the home too. And the second feature corresponding to the first one is that the spectrum resources in a home actually is non-contiguous spectrum bands. It's from TV white space up to 60 GHz radio bands. There are all possibilities to be used in a home scenario. And the third one, as I mentioned in the previous slide, that we have a multiplicity of data services in a home. And the important thing is that all the data services have different quality of service features. For example, the voice over IP and the wireless HD video streaming, they have very different QoS features. So as a result, in addition to the traditional degrees of freedom like frequency, power, and bandwidth, we have a new degree of freedom. It's a choice of the RAT, choice of radio access technologies in home. So in order to tackle this problem, we proposed a framework named Cognitive Digital Home, CDH. And this is a simple illustration of the architecture. There are three major parts. The first one is the Genie node. The Genie node is a simple spectrum manager, and it can maintain the global spectrum information in a home. And also it makes resource allocation decisions and the resource management across the CDH. And the second group of devices are service provision devices. They provide the data service and the multimedia data services for the end users, for the people. And the third group of devices are the relay and the wireless access devices. Actually, they cannot help the service provision devices to provide end service to the end users. and they provide the relay and the internet access service to the service provision devices. Okay, since we incorporate a new dimension of resource allocation here, now we need to kind of relook the concept of resource here. In a CDH, actually, the unit of resource is the three tuple frequency, bandwidth, and rate. For example, here in the 2.4 gigahertz in this region, we may have a channel that's with bandwidth 20 megahertz, and we have a choice of technology there. For example, 802.11. And one thing to keep in mind is that the spectrum utilization efficiency is highly dependent on the technology used on this spectrum. And in this work, we consider about all the possible usable spectrum in a home environment. So the device we consider in a CDH actually is a multiple rads device, and there are multiple rads located on a single radio device. And there are two groups of rads here. The first one are the legacy rads, like Wi-Fi, Bluetooth. And these legacy rads actually can access a limited number of channels in a very specific region, so they have limitations. And usually these bands are overcrowded. And these legacy rads can actually help the low power and low rate device and service. And another group of device is the community radio device. We assume that this community radio device in a CDH can access a channel in an OFDMA style. It means that it can occupy a channel orthogonally, and it can access non-contiguous channels. And this software actually can help us to achieve larger sum rates when the system is feasible. The results about the CDH work actually is published in GlobalCom and WILD, and finally summarized in attribute transaction on wireless communications. And here, since this work is really a traditional resource allocation in a CDH, so I will provide you a summary of the major results in the transaction paper. So in a CDH, we studied the joint channel and right allocation problems. There are two problems here. The first one is a max sum rate problem. So we try to maximize the sum rates across all the devices in a CDH with the constraint of the individual minimal rates and the individual transmission power. And also here we assume that there is a fixed nominal power for each rat. And the second problem is closely related to the first one. It's the max service capacity problem. So we try to maximize the number of the supported service here. And the constraint is the individual maximum transmission power. And we also assume the fixed nominal power for each rat. The reason we assume this fixed nominal power for each rat is that usually this device operates on a fixed level of transmission powers, and also these two problems itself are very difficult. They actually can be reduced to a 2D. They are both can be reduced to 2D multiple knapsack problem. It means that they are both NP-hard. So as a result, we need to develop some efficient heuristic algorithm for this. So we propose a distributed heuristic algorithms. So these algorithms are based on the dual decomposition, and we use the pricing indicators to efficiently manage and allocate the resources. And based on the result of the distributed algorithms, we add another layer, power control, on it. So after we get an initial allocation from the distributed algorithm, that we give a flexibility to the end user to locally optimize their transmission power over these initial allocations. And this addition of the power control actually can improve the system feasibility and the sum rates. And beyond that, we introduce further admission control schemes into our work. When the system is infeasible, so we use this admission control scheme actually to efficiently maintain the system feasibility. And this admission control is based on the price indicators we use in the allocation algorithm. That's all for the CDH work. And this second part is really novel, and it's the effect of end-user behaviors on wireless random access. And here, we try to study the impact of the people's real-life decisions on the wireless systems. The motivation behind this work is actually that we can see the traditional framework design and protocols of wireless system actually they don't consider about the real-life decisions made by people. So all the engineering system designs, the underlying algorithm and the protocols, they are all designed based on the precept of the expected utility theory. So, and the resulting radio resource management algorithm and protocols are also heavily rely on the framework of the EUT. And the expected utility theory, EUT, actually, it is a theory about valuation towards prospects. So people usually will assign a value to alternatives with uncertainty. And with EUT, with this framework, this prospect, these alternatives are valued as their mathematical expectation. But actually, in real-life scenarios, violations to EUT have been constantly observed. So as I mentioned in the first part of my dissertation, so currently the advances of the CR technology and the smart devices and the smart applications actually give the people and the users, a much greater degree of freedom to control the devices. As a result, these people and the users definitely will have more impact and influence on the design, the system performance of wireless system than before. But the current designs do not consider this point. There are many examples here. For example, that as I showed before, that now on single device, the end users may have options to switch among different racks and maybe to adjust the transmitting power. And also, it's possible for users to even modify the radio cards and the underlying protocols. And also, more importantly, end user action in response to the link conditions, to the service qualities, and to the pricing packages is very important in the system performance. Okay, since the prospect theory is a very novel idea, new idea to most wireless researchers and practitioners, so I want to provide you with a short introduction here. It is an alternative way to value a prospect. And before that, what is a prospect? The prospect is a contract that actually use impossible outcomes, for example, from O1 to OM. And each outcomes may have occurring with probability pi. So how to evaluate this prospect? Maybe to put it simply, that prospect is a lottery. And for expected utility theory, EUT, it has been well known that it's proposed by Bernoulli and developed by Van Neumann and Morgenstern and many others. And game theory actually heavily depends on the EUT. And in particular, the current game theoretic models in all these models in wireless networks system also heavily depend on EUT. And as I mentioned before, that the EUT actually evaluates the prospect as the mathematical expectation of values of all possible outcomes. But there are many violations to EUT have been observed during these years. And in order to explain the disparities between the theory of EUT and the violations in real life, Kahneman and Tversky proposed the prospect theory. And actually it is a Nobel Prize winning Nobel Prize award-winning theory. And this theory is shown to be a better theory to describe people's real-life decisions facing alternatives with risk and uncertainties. And it can successfully explain the violations I mentioned. And there are two major features to PT. The first one is that people actually have very poor judgment over the probability. So they subjectively transform the objective probability to some subjective value. And the second feature is that people evaluate the outcomes in terms of relative gains and losses according to a reference point rather than the final set position. So let me explain it in details. So the framing effect is corresponding to the second feature. People evaluate outcomes in terms of relative gains and losses regarding a reference point rather than the final set position. And this is a simple plot example for the value function. We can see that this value function is concave in the gains region and is convex in the losses region. And the important thing is that usually the losses usually loom larger than gains. So for the fifth unit change of the outcome, the value changes in the gains region actually is smaller than that in the losses region.
Sometimes some of your slides use the word valuate, and some slides use the word evaluate. And the question is, are they synonyms, or do they mean something different?
For here, I use them as the same word, but I
think we should fix it.
Yeah, but I'm sure definitely we should differentiate.
So anyway, I wasn't sure evaluate was a word, right? So I went to Google, and it says evaluate is to set a value for, right? Which is not exactly the same thing as evaluate.
Yeah.
So I wasn't asking it as a joke. It was kind of like in this context, are people using the word evaluate to mean something different?
So I've seen it used in both ways to mean the same thing in the context of this, essentially that there is a value that you assign to outcomes. But evaluate is a word.
Yeah.
And in fact, more than value, they use the word valuation. Always the sentence is somehow described as valuation as the word that is actually used. Perhaps we should point this out.
Is somehow evaluate or valuation the word like the prospect theory version of expectation? Does it? Is it? Let's keep going. But somehow, right? People use, you somehow look at outcomes versus value based on this kind of bent curve, right? And somehow I thought, maybe, like the math of how you make decisions on this is is you use the word valuate as opposed to, or valuation instead of expectation, where you use normal, actual probabilities. All right, let's keep going. Maybe it'll become more clear.
I think
Okay.
So the probable weighting effect, as I mentioned, that people actually have poor judgment as a probability. So in a sense, actually people nonlinear transform the objective probability to the subjective probabilities. Some simple examples are the lottery and the insurance. And for the lottery, so you can see a lot of people buy lotteries, but mathematically it's almost impossible in fact. But still many people buy lottery. That's because people have a very poor judgment over the objective probability. So the probable weighting effect here has two features. The first one is that people actually overweight the low probabilities. So it's like in this region. In this region, actually people kind of overweight the probabilities. But people actually underweight moderate and high probabilities. In this region, you can see that the subjective probability here is lower than the objective probabilities. And usually, the probable weighting function here is asymmetric, reflected at 1/e. And the probable weighting function is concave in the lower region, and it's convex in the upper region. But one thing is that people actually are objective to evaluate the certainty. So it means that when the event is impossible, W0 is still 0. But if the event occurs with, for sure, W1 is still 1. And in our work, actually, we use this form, this probability function form proposed by Perlac. And important parameter alpha here characterize the deviation from EUT. And the less the alpha, the more deviated from the EUT. And a special case, the when alpha is 1, it's just the objective probability.
I have a quick question just for out of curiosity. Is this somehow modeling the fact that people do not know the probabilities? Is sort of like an estimation error on the real probabilities? Or is sort of modeling the impact that people give to bad things happening? Somehow they're more, even if it's a low probability, they're more conscious that this is going to have a big impact on the overall utility. So how do you see that?
I think when they proposed the PT, this probable weighting effect, they kind of abstract this effect from many experiments. So so this is kind of response when you feed an objective probability to a human.
So they know the objective probability? Okay,
So
so it's not an estimation error, it's sort of like their perception on how this will impact the utility.
Yeah, I get your point. It's kind of inherent, embedded in the human decision-making process. It's not that people make errors.
So I don't know if it's there in your next slide, but there are two terms that are used. It's there in the next slide, right? No, it's not. So go back to the previous one. So I think what they say is that you tend to be loss averse, and so you sort of have a tendency to overweigh probabilities even though they're really small, because you're sort of scared of losses. And similarly, when you're risk seeking, even though there's a very small chance of succeeding, you tend to sort of essentially underweigh the probability. So that's why if you look at this Mega Millions, right, I think that's what Tianming was trying to say, is that if you buy one ticket and if you buy 100 tickets, the probability of winning is pretty much the same. I mean, you can say it's an order of magnitude.
2 orders of magnitude.
2 orders of magnitude, sorry. Yes. But effectively it's the same. Right? Yeah. So that's how, so people will go buy 100, they'll buy tickets for $100.
But that's, I think it's also an estimation error, because like the general population cannot really estimate the real probability.
Yeah, no, but no, so this theory is based on actually presenting probabilistic.
Right.
So, and also the test set for this was actually students and faculty members at Jerusalem, at Hebrew University in Jerusalem. So these are pretty smart people. So I don't think it's like they went to some average Joe on the street and put in no probability and gave them this problem. So this is sort of even people who really understand.
So it's just a perception that we fear more losses.
Yeah.
But you'd think they wouldn't live in Israel then.
So, but this is, wouldn't it depend on what probability you're talking about? Because people undervalue the probability of a car accident.
Yes.
And overvalue the probability of being in a mall where terrorists attack, So that kind of thing is.
Right. So maybe he will say something about it at the end of the talk. But they are a very good question. It's essentially what are these outcomes?
In connection with money making.
It was done purely with money, but then since the last 40 years, it has found applications in biology,
so for
science,
this
medicine.
Curve that you have,
Yeah.
what would be a typical ideal application for it? What probability are we thinking about?
Yeah, that's correct. This curve actually is a kind of it's based on many experiments.
Okay.
And first they have this curve from these experiments, and then they try to propose different math functions actually to describe this
I
curve.
agree, but what game are you playing? Are you trying to, is it like a lottery experiment, or is it asking some other kind of risk? How was the experiment done?
I will show an example in the following. So
Yeah,
you see
but
it.
to answer your question, this mathematical form was proposed much later, not by Kahneman and Tversky. They did sort of very subjective experiments, and they said this is the conclusion we have. Then people who wanted to understand sort of a more rigorous mathematical framework for this, one of the guys proposed this function. And the key is that if you change alpha, you can get pretty much any shape you want to.
I think
So the hope is that if you...
This kind of shape applies to other human senses also, like vision or sound.
Yeah.
You're initially very sensitive.
Yeah.
So somehow the example, right, of overestimating terrorism is that bottom left corner, right?
Yes.
But somehow the probability of a car accident isn't up at point, it is also, is the other side, but it's not at 0.9 or 0.8. The probability of a car accident is 10 to the minus, in a given year, 10 to the minus 1. It's like 0.1 maybe, right?
Yeah, that's a...
Somehow all those classes of decisions are all
Down there.
way down in this part of it, like
Yeah, that's a good, very good point. Yeah.
Car accident in this area is once in 6 years.
that's good. That means got a couple more years.
Okay. So this is a general valuation of a prospect. So for EUT and PT. So as you can see that for EUT, valuation of a prospect is expectation, mathematical expectation of all values of outcomes. This PI here is the probability event outcome OI will occur. But for the prospect theory, this utility, this value should be modified in two parts. The first part is the probability weighting effects. The weight here is not the objective probability anymore. It's a transformed subjective probability. And the value here should reflect the framing effect we talked about before. And we think about this as the psychophysics of chance of people.
So what Narayan mentioned, risk aversion, is that all in the framing effect?
I think it should be reflected in both the probability weighting and the framing effect.
Oh, okay.
See, the way it works is they first ask questions and they sort of tabulated these responses. And then this is a model that is trying to explain that. So therefore, it's really in both of them. So it's really in both of them. So it's not like these are independent.
So risk aversion causes you to overestimate the probabilities of
Right.
small bad things?
Yes, and also what you think of as risk depends on the value function,
Yeah.
your framing.
So that's
Right.
what I was asking you, but it's not just in the the value
No.
function. Okay.
No, it's not. It's actually both. So there are two things that are simultaneously postulated as a model.
Here is an example. Actually, it is example of real experiments. So usually, they give the students two problems. The first problem that you have two options. The option A is that you may win 2,500 with probability 0.33, or you can win 2,400 with 0.666, or you may win nothing with probability 0.01. And the option B in problem 1 is that you will win 2,400 with certainty, for sure. And for problem 2, there are also two options. The prospect A is that you may win 2,500 with probability 0.33, and also maybe 0 with probability 0.67. And for option B is that you may win 2,400 with probability 0.34, and nothing with probability 0.66. So 61% of the respondents actually choose B in problem 1 and choose A in problem 2. So after some simple calculation under EUT, so the 1B choice actually implies the first inequality, and the 2A choice implies the second inequality. And as you can see, if you look at it carefully, you can see that actually this is a contradiction here. It's a complete paradox here. And the EUT fails to explain this. However, with the help of PT, if we plug alpha equals to 0.5 in the utility function of PT, these two inequalities actually can be established simultaneously. It means that PT actually can explain this phenomenon.
So here's an interesting data point. Right? So I gave this talk at Comp Theory workshop. There were about 100 people in the audience, all comp theory and communication theorists, information theorists, and they actually voted.
Yeah, I heard reports that
You heard
everyone
reports.
agreed except for Andrea Goldman.
Right, Andrea Goldsmith is the only one who was not fooled by this paradox, but pretty much 2/3 of the audience said exactly, what most of us would say, and you'll see that as part of the paradox, where you end up choosing sort of the opposite sides of. If you're following sort of EUT, you would make consistently one choice, right? So it's essentially sort of, and there are many, many examples like this. In fact, they have Kahneman and Tversky have a book which is full of examples.
So with money, I can see that.
Yeah, but you can
When you
impose
apply
it.
it to other things,
Yeah, you have to become, now you need to figure out what is that.
the
I agree with you. That's very important. In fact, that is really needed.
Right, so this one, presumably there's some min-max calculation that it will make also.
Not so much, I think it's just like
Maximum loss of 2400 seems too much.
So actually the failure of EUT in describing this does not mean that people are not rational. So it just means that EUT is not able to describe the people's real life decisions, but PT can. So we try to tackle this problem, the role of PT in wise networks from the toy problem, wise random access. So here, we assume that there are a set of unselfish players accessing the same base station, and they all try to access in the same band. And they access this resource with a time-slotted and synchronized style. And each player has a saturated queue of packets, so it means it's always ready to transmit. And in each time slot, a player can either transmit or wait. It means that she has two actions. One is T, means transmit, and NT means not transmit. So this lowercase r a in bold is the pure strategy profile vector, and the uppercase a in bold is the collection of all possible pure strategy profiles. In each time slot, if a player chooses transmit and this transmission is successful, this player will obtain a unit throughput reward and incurs a unit energy cost. But if the transmission is failed, she will incur a delay penalty, unit delay penalty DI, and a unit energy cost. But if this player chooses to wait in this time slot, she will get a minus DI, I mean a unit delay penalty for sure. And for both PT and EUT here, we assume players use the same value function here, and we assume a linear. This function actually is a linear in unit throughput reward delay penalty and energy cost with the reference point set to 0. And this is a value function for the ith player. This JA means the set of players who transmit in this slot. And we can see that if the ith player chooses to wait, not transmit, she will get a minus DI, delay penalty for sure. But if she chooses to transmit, she will get this value. And there's possibility the transmission is failed.
So you keep using the word unit. So suppose I left the word unit out of this slide. I just retained a throughput reward, CI, and energy cost, EI. Would anything change? What's the word unit mean in this slide?
So actually, it it kind of, if you transmit one packet, so the throughput, if it's successful, the throughput reward you get is a unit throughput reward CI.
Well,
But
is CI a number? Like you get,
Yeah.
is CI equal to 1, or is CI equal to some reward value associated with one packet, like, reward 33 cents?
CI can be a varying values, but it's I'm not sure it's definitely mapped to a monetary units.
Like
Here,
if you
unit
use-
really means packet, that's all, per time slot. If you do one packet, you get CI. We call that as unit.
So it just means it's a reward per packet per time slot.
Yes.
Okay, so it wasn't like somehow to say, oh, the throughput rewards have one kind of unit and the energy, because throughput rewards are in bits or packets or something, right? But energy's in joules. Is it? I was going to ask the other question: is were you using this terminology to say, oh, you can't compare the CI and the EI, or they might both be numbers, but they're different units?
We try to set them in the same context. Otherwise, it's at this stage we try to strip off all the unnecessary complications just to find out the joule.
I think the use of the word unit here is it's confusing.
Okay,
As
so
opposed
maybe we
to
should
per
clarify
packet.
this.
Yeah. Okay, go ahead.
So maybe it would be a unit of transmission, maybe per unit transmission. That would be more,
Yeah, maybe.
because I think that he refers to unit here as the packet. So,
And it's a packet, and there's only one packet per time slot in the whole model.
Yeah.
Yeah.
So, but I think that we should clarify. So it was not,
I guess I think you could just leave it out and just somehow write one sentence that says all rewards are on a per packet per time slot basis. And maybe it'd be more clear. All right, okay. See, the problem is when you write a thesis in something new, right? You have to look at all the words and think, because some of the words you use don't, like subjective probability really means something. So it's hard to tell when words have new meanings.
So, and this framework that we can we can have the utility functions for EUT player and for the PT player. And for EUT player is just an objective expectation of values of all possible Q strategy profiles. But for the PT player, we see that there are differences here. When the player actually chooses to transmit the value of this strategy profile is weighted by this SPA1. It means the subjective probability the ice player gave to the strategy profile A1. And then you can see that the ice player actually nonlinear transform all her opponents' probability here. This Wi and this Wi here. Okay, with this set, the first thing we try to study the consequences of deviation from EUT. The first game we study is a two-player heterogeneous game. Heterogeneous game, it means that one player is the PT player and the other one is the EUT player. And we try to find out the impact the PT player introduced to this game. And the first thing is the performance change of the EUT player in the heterogeneous game compared to the traditional EUT game. And the performance difference between the PT and EUT player in the heterogeneous game. And finally, the overall system performance disparities between the heterogeneous game and the EUT game. And the metrics we study here are average energy, average throughput, and average delay. So since we study a two-player game, we can spell out all these formulas here. And this for PD, this is the utility function for the PD players, and this is the utility function for the EUT players. And the matrix mentioned in previous slides is this is the average throughput. This is the average throughput for the S player, and this is the average energy cost for the S player, and this is the average delay penalties. So for this game, we actually proved that there exists a unique mixed NE in this heterogeneous game, given these two conditions are met. The first one is that the value of a collision-free transmission is actually positive, is larger than the reference point. And the second condition is the negative value result when there is a collision. It means the simultaneous user transmissions. And this negative value minus di is actually the value the player obtains when she chooses to wait in the time slot. Okay, we have observed and proven these consequences of deviation from EUT and some mild conditions. So the consequence one is that the PD player, the introduction of this PD player actually causes the EUT player in the heterogeneous game to gain higher average throughput, to experience less average delay, but to incur higher average energy cost. And the second consequence is that the PD player itself in the heterogeneous game actually achieve less average throughput and experience greater average delay than the EUT player in the heterogeneous game. And the consequence 3 is about the system level performance degradation. So the heterogeneous game, due to the introduction of the PD player, achieves lower total average throughput, great total average delay, also incur higher total energy cost. And all these consequences are exaggerated with a lower alpha, which means that when the PD player deviates more from EUT, these trends are exaggerated.
So in the first consequence, the PT player being PT rather than UT is causing this suffering, these consequences for the UT player, right?
Yes.
In the second case, it's the PT player, he achieves less compared to what? Compared to being UT himself?
Compared to the EUT player in the game, per opponent.
Okay. And then finally, how come consequence 2 has no energy consequence?
There should be that here that the energy of the PT player is energy cost is actually lower than the EUT player.
So the PT player is lower than the UT player, but is it lower than what it would be if the PT player were also a UT player?
He's asking if it was homogeneous.
Well,
If you
like,
compare-
is it? I guess is it? You know, I thought you were okay. So you're saying the PT player uses less energy than the UT player.
Yeah, in the same game. Yeah.
It's to parallel the description of the other ways in which things are less or more. So I have one more question about this, which I couldn't figure out reading the thesis. Does the UT player know that the PT player is PT? And does he put that into his calculations of what he'll get, of what he should do?
So if you go back and show the math and explain who knows what. Yeah, from here.
So I think this is really about the concept of the mixed NE. So in a game, actually, when all the players arrive at as a mixed NE, actually, her probability, for example, PI, actually makes her opponent kind of indifferent between transmission or waiting. So it's not necessary that for example, for the EUT player to know the PT player is a utility function. One thing the EUT player needs to make sure is that her action, her probability, need to make the PT player indifferent between transmission and waiting. So
the UT player's choice makes the PT player indifferent to transmitting or not?
yes,
Indifferent with respect to
the value.
the
You should get the same value whether you transmit. What is an Nash
But the
equilibrium?
value is measured by the PT player.
Yes.
Or
But it's not necessary you know the utility function of PT player.
But to do all the solutions that you have done have assumed sort of complete knowledge of everything.
Yes, usually that's an assumption for all the game theoretical
Yes, the
models.
way you sort of solve all these equilibrium conditions. I mean, to do any kind of numerical solution, right? You sort of assume that you know everything already.
so in
He's assumed
essence,
everything.
the UT player
Absolutely. So
it
he
knows
exactly.
how the PT player values things and
He just
how-
knows essentially his value function. Let me put
right.
it that way.
Yeah, for every
That's all.
possible
Yes. Yes. Now.
strategy
Yeah.
there or
Exactly.
whatever.
Yeah. But how it came about, that's not really taken into account. It's just that you know the value exactly. If I take an action, I know what value you will get. If I take another action, I know what value you will get. I know that.
in the way I measure value.
Yes.
Yeah. Okay. So.
So this is some numerical simulation for the above consequences. And we can see that the introduction of PT player actually makes the EUT players gain more average throughput. It means that this green line is actually...
So what's the channel here? You should say that first.
the channel here is that for collision-free transmission, the package reception probability is 0.98. But for a collision transmission, the probability of a packet reception is 0.05 for both players. And we can see that this green line actually represents the EUT players in the EUT game. So it means the traditional game. But with the introduction of the PT player, you see that the average throughput of the EUT player actually kind of increase. And you can also see that, for example, this red line is the PT player's average throughput, and this dotted red line is the EUT player's throughput. You can see that obviously the PT players achieves less average throughput than EUT players in the heterogeneous game. And as you can see that as alpha becomes smaller, which means the more deviation from EUT, that this trend is more exaggerated.
So the UT player does better as alpha gets smaller. Is that right?
Yes. In terms of individual average throughput, this is true.
So why did you not go to like alpha is 0.1 or?
There is a limitation about the prospectivity. Actually, we should not push alpha to 0. So
No,
an
but
extreme
why not 0.1? You could have done 0.1.
0.1 and the alpha, this value, I will mention it in the following slides. Actually, they are heavily dependent, abstract from the real experiments. So theoretically, we can push it to 0.1 or 0, but in reality, I don't think it makes any sense.
But those things are based on money, not on data.
Yeah, you could have very well plotted something for alpha equal to 0.1, in my opinion, because I don't think we've done any psychophysics experiments. I mean, Ray asked the question, right? He said whether you tell somebody it's an accident, or you're going to die in a plane crash, or whether you're going to win $100, the way they view these problems are very different. So we need some wireless, sorry, we're going to talk about it at the very end.
Wireless psychophysics.
Yes.
Yeah. So I think one interesting fact about
So for this curve, you could have very well plotted 1 for alpha equal to 0.1. You would have seen it's lower.
yes.
It's monotone. As you keep sort of pushing alpha down, you'll see that it does that.
Actually, if alpha for a person is equal to 0.1, it's a very tragic event for this person. So this is the sum throughput comparison. So the green line represents the traditional EUT games. Both players are EUT, and you can see that obviously that the deviation of PT player actually hurt the system performance in terms of throughput, average throughput. And as alpha becomes smaller, I mean more deviation from EUT, this trend is more exaggerated.
What is the x-axis of these plots actually? Like is it C over E? What is it?
So here we fixed E equals to 2, and we varying C as multiples of
E is
E.
like the energy cost of sending a packet,
Yes,
and
C is the throughput reward. So we try to see the trend when the values vary.
so wait, so C is the throughput reward,
That unit is throughput reward.
and so somehow all the throughputs are higher. Am I wrong? When the reward for sending a packet is small, and as you increase the reward, the throughputs all go to hell. Like,
That's because that's 1C. The unit throughput reward is large. The players actually kind of become very aggressive in transmission. So it means many conditions there. So your effective throughput, I mean good put, is very, very low.
so if you try not to care, everyone does better, right?
So like example in my proposal, for example, people, if there is traffic jam on the highway, people
Right.
just desperately access the cellular service there, but no one can get any data, but people still access the data service anyway.
Yeah.
So that's some scenario in this region. I mean, because people are boring, so the throughput reward there is very large. So this final plot is energy cost comparison here. And the important thing here is that the upper part is the total energy cost.
But wait, what happens to that plot if you went more to the left? Like so if you go to, you stop it at 2, right? If you went from 2 to 1 to a half, like is it at less than 1, you just never translate anything and it's back to...
I actually have a plot, for this part you mentioned. And also, there are some conditions. So we actually prove this thing, this result, under some mild conditions. And the value, why I take this value is actually to meet some conditions. These conditions are specified in the dissertation. And you can see that because of the...
So but to answer this question, if you go there, what happens?
If you go there, that's the same trend. The PT game still achieve less sum throughput.
Well, okay, so but all the curves kind of are merging there too, right?
So he's saying
So the question is, what's the
go up
shape
or the
of
short?
like all these
It
curves?
should be like this. So there's a global optimal point there, although it's very hard to prove.
Yeah, please.
Yeah.
Now I just see the next result.
So this upper part is the total energy here, and you can see that the PT actually also caused the whole system to consume more energy here. So the second game is the homogeneous game, and the homogeneous game means that both players are either both PT or either both EUT, and it's true that mathematically that homogeneous game is heterogeneous game is a special case of homogeneous game, but they carry different physical meanings. So for the homogeneous game, that we have these two consequences. The consequence 4 is that system level performance degradation. That on the system level, that the homogeneous PT game actually achieve lower total average throughput, but have a greater total average delay and higher total average energy cost. So it hurts the system in every aspect of the communication. And then,
So consequence 4 is saying that if the two players each become more PT, like alpha gets.
Forget more. It's
Become-
EUT versus PT.
So if the two players are both PT, they do worse than if they're both UT.
yeah.
Okay.
So ideally, right, you would think if everybody's, people behave subjectively, and we have to assume everybody's behaving subjectively, which means that the entire system is bad. Right? That's sort of what it is. Yeah.
So the consequence 5 is about the two PT players in the same game. So in the same game, that's the PT player who deviates less from EUT actually do better in general. She can achieve more average throughput and suffer less average delay. But actually, she incurs more average energy than her opponent. So this is the plot for the individual average throughput for the two players. And you see that when alpha equals 0.8, this curve, this player is less deviated from the EUT, and she achieves more average throughput than her opponent. And this is the sum throughput comparison. And the blue line is the homogeneous EUT game, and the red line is the homogeneous PT game. And there's an obvious degradation due to the deviation of the PT players, both PT players in the game.
So is the left-hand point still C over E equals 2?
Yes, I think so. It should be start from 2.
It doesn't look like 2, basically, like it looks like 5 to 10. That doesn't look like.
It does look like 2.
I think it's 2.
Okay.
Yeah, it seems a little.
Yeah.
I think it's 2.
Can you mathematically prove that they're the same? Are they in fact the same at 2, or is it that one is they're just close?
This global, this point, actually, this is very difficult to prove. You can see the shape of the curve here is not concave. And also keep in mind that the probability, transmission probability at the mixed NE is also a function of C here. So it's highly coupled with each other.
So really, there's two questions in that point at 2, right? One question is like, is that kind of some kind of an optimum, right?
Mm.
Is it right? And the other question is it in fact true that the two systems have the same performance? Like the red dot and the blue dot are in fact the same operating point at 2.
You mean whether these points are the same?
Yeah.
This one,
Or is it just like a miracle that they just happen to be right next, like almost on top of each other? But
I think it's probably, I don't know if you can prove it exactly, but if you have two users and they have a utility of 2, probability of transmission about half, something like that.
well, yeah, that's what I'm kind of asking. Is there some fact out of the numbers that gives 2 this property that the the users are actually behaving identically?
So I think the thing that he tried to say, and I don't know if you came across it, is that when C over E is not 2 or less than 2, he cannot even prove all those statements he just said.
Right. So
Because there's
in
some
some
conditions
sense, 2 is some special boundary.
For this number, for this
Yeah.
set of values chosen.
Right. But so the question is it that
Yeah.
because of that,
Should check
is
it,
it
it's
that
same.
that it has some magical property in terms of making those two systems be the same?
there's a point where EUT game and the EUT player and the PT player choose the same transmission probability. But whether it is corresponding to this point, it depends on. And the results here actually are theoretically proven in the dissertation. I mean, for
Yeah, no, we
theory.
understand that, but he's asking besides the proof of, we understand the conditions under which we prove it, right?
Yeah.
But really, given that it seems like the last 4 plots pretty much had this property where they're sort of same at one point, and his question was, is it really same or is it just sort of something pretty close?
Does it have anything to do with the fact that you mentioned in the very beginning that it's the certainty and the impossible event they evaluate well? So as you go towards these points, they kind of converge to the same thing.
No, this is for a fixed alpha.
That's what fixed alpha.
Yeah, what's the alpha here?
The alpha here is that for the PD game, actually one alpha is 0.5 and one alpha is 0.8.
But it seemed like from some of your other curves, it was even insensitive to alpha. It seemed like they were all kind of matching up
I
there.
think it depends
Maybe
on
some phenomenon like what Ray said.
0.98.
Or
Like
0.05.
classic random access.
Yeah, at some point where the numbers are such that like everybody transmits
2
with
and 1/2
equal
cancel
probability.
out then.
That's the difficult part of this, because everything has a role in the final value function for strategy profile. And that's why I proved this everything under the conditions of the value function, values given fixed outcomes. And in the simulation, it's very difficult. You try to manage so many dimensions in the same plot.
Yeah, but I think
Okay,
we should try to find out an answer.
Yeah, you can.
I agree.
Let's go to the end.
Okay, this is the energy cost in the homogeneous game scenario. So you can see that the PD game actually consumes more energy cost, as I mentioned. And we extend this 2-player homogeneous game to the n-player scenario, and we assume symmetric utility functions for all the players. And why we assume this is because this actually reflects a scenario that each player has a collective view of all her opponents. Since we as I mentioned, that the people have the bounds of rationality, it's very difficult for each player to analyze each of her n-1 opponents' utility functions and actions. It's beyond each user's feasibility. So this kind of a software actually can simplify the job for each player a lot. And we prove that under this assumption, there exists a Unix mixed NE. There still exists a Unix mixed NE for the symmetrical n-player homogeneous game.
So what's the definition of mild conditions?
It's in the dissertation, and
Yeah, but it's subjectively, physically, what is it?
it's that the utility function, first the utility function should be a decreasing function of your opponent's transmission probability and the increased function of your opponent's transmission. This is always maybe in EUT, but in PT it's not that straightforward. And another thing, the same thing applies that when there is a collision. Yeah, I think that's the conditions here.
Yeah, it's very intuitive. It just says if you increase your transmission probability, I think there's an expectation and my thing is going to go down.
We would have done it decreasing.
So here is a plot for the simple 3-player homogeneous game. This is a average throughput comparison, and you see that there's a degradation in terms of the average throughput. So you can see the gap here. But for anything beyond 2-player, it is very, very difficult to prove. So, okay, so in the second part, we hope that everyone have seen that the people's real-life decision actually can impact and influence the underlying system design. And more interesting, maybe question is that how will this deviation from EUT will influence the data pricing? And as I mentioned, that prospect theory is heavily, initially proposed based on monetary transactions, and the data pricing is this field in wide systems that end users make monetary decisions. So here we consider a simple two-level pricing model. There is a service provider, and there are a group of end users. And the service provider actually announce the prices charged for the usage to all the end users. And when all the end users receive these announced prices, these end users will choose their transmission probabilities based on the throughput, reward, delay penalty, and energy cost, and also this newly announced price. So this is a model for the pricing scheme. That's at the service provider level. That this service provider actually tries to find out the optimal price vector charged to all the end users to maximize her revenue. And the end user level, that I use the same wise random access game in the end user. So this end user will choose their transmission probabilities depend on the factors I mentioned above. And this model actually can be modified in a more general form. It should not be just limited to the wise random access game here. And I start from the two end user price model. One reason is obviously is due to the mathematical intractability of the PT utility functions. So we compare two pricing schemes, UBP and TBP. UBP stands for usage-based pricing. It means that end users charged by usage. So this is a value function for the end user for collision-free transmission. And this is a value function for the end user for collided transmission. And you can see that even if the transmission is failed, a price is still charged for the IC user. And this is a utility function for the PT end user. And mathematically, UT player's utility function is a special case of this one, when alpha is 1. And this is a utility function for the service provider. And you can see that her revenue is generated from the actual usage of the service. And the actual usage of the service is reflected in the transmission probability. The second scheme is the throughput-based pricing, the TBP, and the users is charged only by effective throughput, good put. So we can see that from the value function shown here, that if the transmission is failed here, there's no price charged here. And similarly, we can define the utility function for the PT user and the utility function for the service provider. And we can see that the first service provider utility function is only generated from the good put. This is actually the effective throughput achieved by the IC user. So we have seen that we want to see the communication performance under the pricing schemes. And as you can see that under the pricing schemes that the PT users still degrade the performance. The UT users, they can achieve a higher average throughput. This is under the UBP, usage-based pricing. And the case in the TBP, throughput-based pricing, is the same. And although the shape is different, but the UT users, they can achieve a larger average throughput, total average throughput than the PT users. And finally, we want to see the service providers' revenues comparison here. And for the usage-based pricing, so we can see that when the price is relatively small, that the the PT user generates more revenue than the EUT players. But when the price is relatively large, this trend is reversed. And there is a global optimum price the service provider can collect in UVP here. And the optimum revenue the service can collect from the PT is slightly larger than the case in EUT. And for the throughput-based pricing, these two curves, we can see that the EUT always generates more revenue than the PT users. And there is an interesting property here that for the service provider, she can still find a global optimal price to charge to get the most revenue, and it's very close here. So it means that for the service provider, if she chooses the throughput-based pricing, the disparities between the PT user and the EUT players is not that different.
So is it a function of these parameters you've chosen, or is it something you've observed sort of in general?
I have run many simulations, and I try to theoretically prove this, and think it's probably true for general assumption. But yeah, it's not an excuse, it's a real limitation here. It's really difficult here. And here, because the price R here, and the transmission probability, you can say the utility function. The utility function here and here are function of R and PI, but they are not separated. They are coupled here. The PI is a function of Ri. Actually, it's a nonlinear, non-concave function of Ri. So although the general model we consider about always two-player model here, but any assumption underlying the UT, traditional assumption underlying the UT is not naively true in PT. You have to be very careful about this. So this is about the pricing part. And finally, this is very interesting, I want to show some future work based on the part 2. So the last part, I talked about some initial effort in the data pricing field. And in the future, actually, we want to actually develop a more advanced differential pricing data service for network congestion. So what we want to incorporate the end users' effects into the new novel data pricing schemes to efficiently manage the resource. Currently, no mechanism actually consider the end users' effect. And the self-organizing networks, it is a combination of the heterogeneous networks. There are many different technologies, and they are all different people here. But we want to, maybe in the future, we can study as an organization, as a group of people. So how do they react? How do they behave in the self-organizing networks? And also, this is a directive review of the model here. When some users are malicious in the wireless random access networks or in general wireless networks, how do we design effective mechanism against them? I mean, assume that the underlying entities are human beings. And the fourth one is that is very important. We have seen the different disparities here. What we want to do is that we try to develop some robust mechanisms actually to mitigate this user interference. We want to make the system more efficiently. How do we design some novel mechanisms incorporating all the things I mentioned above? And this one is actually kind of corresponding to the TBP results I shown. Is that possible? We can identify some existing mechanism that actually do very well even when the users are PT. So we need not to do a lot of modification. There are tons of pricing schemes in research field and also in the practice, but is there any existing pricing schemes that actually can help the PT users behave very close to the EUT users? This is also another interesting direction. And finally, it's also very important is the psychophysics experience of WISE users. And we hope our work can motivate new researchers to do some more field experiments, actually to more precisely model the probability weighting and framing effects based on the real WISE experiments. So currently, the alpha, the value function, we set it based on our assumptions. But maybe after this field experiment, we can get some real value, and then it makes more sense actually to better design this model. So these are all possible directions based on the part 2 of my dissertation. Okay, I think that's all my research work here. But here, this part is very important. Although there are not many people here, but I want to express my appreciation to all of you. So the first is my advisor, Professor Narayan Mandayan, and I want to thank him for the consecutively intellectual and financial support over these many years. They are both very important, and we have many inspirational discussions, and especially the second part, this PT, we think is very novel and very interesting, and we hope that we can encourage many researchers to do some research work in this direction. And I also want to thank the Professor Ray and Professor Yes and Professor Christina to serve as my committee members. And I want to thank the whole WinLab faculty. Actually, I asked many questions to the whole WinLab faculty, and it's a very good environment that you can get all different kinds of inputs. And of course, all the staff members, Noreen and Elaine, and all the members and James, they are not here, but thank them for babysitting us, the PhD students, for this many years. And all my WinLab colleagues, and I think many of my friends are not here, but at least I see some of them. And I think that's it. And yeah, that's all.